So, welcome to lecture 3. So, in the last class we were studying about, we were developing some language of thermodynamics. We said what are various different types of systems, isolated or closed, open. We have also made the connection that all the material synthesis is going to be an open system where I am going to exchange both mass as well as energy with the surroundings, and that is how I can do material synthesis, right. We defined what equilibrium is, okay. But just very in a very quick way we have defined that, okay, if temperature of system equal to temperature of surrounding, pressure of the system equal to pressure of the surrounding. So, that defines a mechanical equilibrium, thermal equilibrium, and then we said chemical potentials, once I equate them, that defines a chemical equilibrium. So, by equilibrium I mean all the three, right. By system being in equilibrium with the surrounding, I mean that all the three are in conditions are satisfied, and then there is nothing that is happening, right. So, in some sense I gave you the sense that there is nothing that is really happening in the system has equilibrated with the surroundings and so on and so forth, okay. So we defined some conjugate variables, the cause and effect relationships, but let's try to delve a bit deeper into this idea of equilibrium, right. So, equilibrium, right. So, when so this room is at a temperature of 25 degrees Celsius, let us say, right. So, I have defined a temperature for this room, and so every particular element in this room is in equilibrium with every other particular element. This particular volume that I am just vaguely drawing here, right, is in equilibrium with this particular volume, right. Does that mean nothing is happening in this room? No, right. So, there are a lot of air molecules that are moving, nitrogen, oxygen mostly, right. So, that are moving around, and there is a lot of dynamics that is happening. It is not that equilibrium is a dead state, as I have sort of indicated in the previous class, but there is a lot of dynamics that is happening, okay. Now, what describes this dynamics, right. So, what describes this dynamics is a bit of statistical mechanics, right. So, thermodynamics, according to thermodynamics, this room has one temperature, and that temperature defines for me, right. Temperature is an equilibrium quantity. I can define temperature only when something is in equilibrium, right. So, only when a system is in equilibrium with the surroundings, I say that the system has the same temperature as the surrounding. Same thing as pressure, same thing as chemical potential. If a system is not in equilibrium, I am unable to define exactly what the temperature of that system is, okay. So, what is this temperature? Where is it coming from, right. So, how is it that you are able to define temperature for something which is an equilibrium system, and equilibrium system is something that I sort of said that equilibrium systems are dead, right. Turns out they are not dead, right. So, there is a lot of dynamics happening, right. So, that is what we just said. And what is this dynamics? How can I then understand equilibrium system, right. So, the formalism for equilibrium systems then comes from a bit of statistical mechanics. And in statistical mechanics, I am not going into details of statistical mechanics. The next 10 minutes is the only stat mech I am going to do in this course, although you may want to realize that thermodynamics actually emanates from statistical mechanics, right. I mean, although historically thermo came first, then stat mech came next, but stat mech explains the microscopic picture of what thermo takes for granted, thermodynamics takes for granted, okay. So, so statistical mechanics, so what is the microscopic picture of this room? This room has, or what is the atomistic or molecular picture of this room? This room has a lot of molecules that are moving around at so every molecule has a certain energy, and all these are free molecules. So, the only form of energy that all these molecules have is kinetic energy, and kinetic energy for per every molecule is half mv square, where m is the mass of the molecule, right. So, mass of every molecule. So, then I am going to look at some average kinetic energy, that is half m average v square, that is assuming that all the molecules have the same mass, okay. So, this is the average kinetic energy of this room. So, every molecule is moving with a certain velocity, right. Let us say every identical molecule, right. So, this has just nitrogen gas, let us say for simplicity, okay. So, then if I actually look at, then does it mean that every molecule is moving with the same velocity? That is not true, right. So, every molecule has some kinetic energy, but there is a distribution of this kinetic energy, and if I look at this distribution of the velocity of a molecule, right, velocity of various molecules versus how many molecules have that velocity, right. So, velocity has a direction also associated with it, right. That for equilibrium systems follows this sort of a bell curve. Let me draw the bell correctly, right. So, that for equilibrium systems follows this bell curve or a Gaussian, oops, okay, a nice Gaussian, right. And this kind of a distribution, this is a bell curve. This is the probability of finding a molecule with a velocity v, right. And this kind of a bell curve. So, these sort of a distribution. So, I have molecules that have very large velocities, very large positive velocities, very large negative velocities. I have molecules with velocity this, but that comes with a probability of this, right. I have on an average the molecular velocity is 0, right. So, for every molecule that is moving this way, I have a molecule that is moving the other way, right. So, so this sort of a distribution is what is called Maxwell-Boltzmann distribution. Okay. So, as per statistical mechanics, I am saying that the gas molecules in this room are at equilibrium with each other, right. Every volume in this room is in equilibrium with every other volume in this room, any volume, any representative volume, only if all these gas molecules are following this velocity distribution given by Maxwell-Boltzmann distribution. Okay. Now, so what is the average velocity of all molecules? The average velocity is given here, the average velocity is 0, the average velocity of this Gaussian. So, that does not mean that molecules are not moving, molecules are moving in a random fashion such that every molecule that has a positive velocity is being cancelled by every other molecule that has a negative velocity. Okay. But average does not define much in a Maxwell-Boltzmann distribution, right. Now, what is the average kinetic energy? The average kinetic energy we said is half mv square, or in some sense this v square term, the average of v square is nothing but so this is the variance of velocities or root mean square of velocities, however you may want to take it, right. Now, that is given by the width of this curve, right. So, the square root of variance is given by the width of this curve. I have this curve, I look at the width of this or the FWHM of this curve, that gives me the FWHM or the standard deviation, right, that is proportional to v square. Okay. Now, I have to still define a temperature, right. Temperature is not something fundamental in statistical mechanics. Now, I have a distribution with this kind of a kinetic energy, then I say that k times T is nothing but my average kinetic energy, right, or the temperature of this room. Now, I am going to define the temperature of this room, k being the Boltzmann constant, k is the Boltzmann constant. That is why this is called a Maxwell-Boltzmann distribution, right. Actually, there is some interesting story about Boltzmann, so Boltzmann had become really depressed that his theories were not being accepted by the society. So, so it is a sad story, it ends on a very sad note, but so the realization about Boltzmann theories, Boltzmann definition of entropy, the transport equation that he gave later on, all this realization that these are actually correct and still used to this date, right. So, in everyday research is a testimony that so he is sort of ahead of his time at that point. Okay. Anyway, but that's a digression. So you have the Boltzmann distribution. So, from the Boltzmann distribution I can define the temperature, right, and temperature goes as the standard deviation or so the variance of this Gaussian, right. So, I have a Gaussian distribution, and if I can define the variance of this distribution, then I can define the temperature for this system. So, the temperature of this room, right, is nothing but the variance is related to the variance of the velocities of all the molecules in this room, right. Now, so first of all, this equilibrium in this room as per StatMech comes from a distribution. and that distribution is Maxwell Boltzmann distribution, right. Now if I have electrons in my system, right, so it is not really air molecules, but I have free electrons, let us say. Okay, so in some system, some 2D electron gas, I have free electrons. Now I want to define the temperature of these electrons, right. So these electrons then, so electrons are what are called fermions, so they follow what are called Fermi-Dirac statistics. So if I have electrons, the velocity of the electrons following Fermi-Dirac statistics, from these Fermi-Dirac statistics I can define the temperature of the electrons, right, as so you can imagine that this is an electron gas, just like we have the normal gas here. Okay. Then if I have phonons, or if I have some photons or photon gas or something like that, I can define T photon or T all these are bosons, right. So they follow Bose-Einstein statistics. This is just to introduce you. I am not going into details of what these statistics are, because this is not a StatMech course, but so temperature is something which is not fundamental in statistics, in statistical mechanics. It is defined for equilibrium systems, and equilibrium system should follow one of these three distributions, right. So everything is a distribution, and equilibrium systems either follow let me rewrite it, equilibrium systems in StatMech definition of equilibrium systems is they either follow Maxwell-Boltzmann or Fermi-Dirac or Bose-Einstein statistics based on what type of particles these are. These are for classical particles, these are for fermions, also quantum particles, and these are for bosons. Okay. So if my particle distribution is one of these three distributions, right, in a room or wherever these particles are, then I say that all right, so these electrons are in equilibrium with each other, right. So that is the definition of equilibrium from statistical mechanics. Okay. It is not that the electrons are not moving, it is not that the air molecules are not moving, the air molecules are moving very vigorously, right. So if I increase the temperature, what happens to the Gaussian? So this is Gaussian at a lower temperature, let us say. If I increase the temperature, the variance is going to increase. This is T1, this is T2, right. T2 is greater than T1, right. So the variance is going to increase, which means I have more molecules that are going at much higher speeds, right. Speeds is okay, but on an average their velocity is still 0. So average is not changing, but the temperature has changed because the variance has changed. Okay. So temperature is a derived concept in that fashion from statistical mechanics. In thermodynamics, however, we assume temperature, which is a measurable, I can measure the temperature, right, as something which is very fundamental, right. But if I further look into the problem and further fine grain it, I go into the realm of statistical mechanics, and in StatMech temperature is defined for equilibrium systems, number one, right. Equilibrium systems, you can define temperature. Same thing with pressure also. But however, so this is defined based on the distribution, right. So if it is a Boltzmann distribution, then KT is just half mv square. Based on that I can define what temperature is. Okay. All right, good. So having said that, now so what is a non-equilibrium system? We know what an equilibrium system is, right. So what is a non-equilibrium system, for example, right. So if I take your plasma in tokamak. Tokamak, what is tokamak? Tokamak is a nuclear fusion reactor that several countries are putting or have been putting their efforts into to generate energy using nuclear fusion, and in nuclear fusion you are creating a plasma, right. Inside the reactor there is a plasma, and this plasma is heavily non-equilibrium plasma. By non-equilibrium I mean, if I look at the velocity distributions as a function of if I look at the velocity distributions, the probability of velocity versus velocity, it is no longer my Maxwell-Boltzmann distribution. I have some sort of a bimodal, trimodal, whatever it is, right. So I have distribution. This is a non-equilibrium distribution. Right. And in non-equilibrium distribution I cannot define a temperature. Right. Even in your growth processes, right. So sometimes you use plasma, right. or material synthesis processes use plasma, right, and this plasma, so if it is a low energy reasonably, so if I am using something in a process called PECVD, plasma enhanced chemical vapor deposition, right. By the way, we will look at what this chemical vapor deposition is as part of case studies, right, but so this is a process in which I create plasma using some precursors, and this plasma enhances some kind of chemical reactions that happen on your substrate to create a film of your choice, right. So essentially that is a PECVD process, and this plasma is a low energy plasma, right, some EVs or something like that, you can set the energy, and so you can actually define a temperature for this plasma. I can define a temperature for this plasma. The higher the energy of the plasma is, right, the difficult it becomes to sustain a Maxwell-Boltzmann distribution, and it goes away from equilibrium. So I cannot probably define temperature of a very high energy plasma that is used in pulsed laser deposition, right. So pulsed laser deposition is another process, right. So in this process what I do is I have a target, again this is a thin film deposition process. I have a target, and this target has a material of interest. Let us say I gave you one material of interest, which is barium titanate. I am going to hit this with a laser, a pulsed laser, a UV pulsed laser, right, and this UV pulsed laser gets ablates, so this target, which means part of it is absorbed, and then it evaporates, and in fact it is not just evaporation, it is creating a plasma state, right. So evaporation plus a lot of electrons and so a lot of charged particles, that creates a plasma, right, and this plasma is going to deposit on your substrate. So on your substrate, so this is a substrate, and I want to grow a thin film on my substrate. So the reaction on the substrate is plasma is giving rise to a solid, right. So this is plasma phase to a solid phase, solid thin film, right. Now this is going to be this plasma, so it is not very easy to understand the thermodynamics of this plasma, because it is a very depending on its energy of course, but most of the plasma that is done in everyday PLD is a non-equilibrium plasma. So I will not be able to define the temperature of this plasma, for example. So I will not be able to treat it in a very thermodynamic or an equilibrium framework. Okay. Now having said that, of course life is always not very easy, right. So we are let me insert, okay. So life is always not going to be very easy. So let me give you this example, right. So but does it mean that I am not using thermodynamics in non-equilibrium systems, right. So that's does it mean that I cannot define a temperature, right. So I can give you a very easy example, right. So I said temperature is only defined, right. Now so far the statement I made is temperature is only defined for equilibrium systems, right. Now this is not necessarily always a correct statement, because look, alright, so I come from some kind of a heat transport background, let us say I give you a rod, right. This is a problem that we give in our interviews, right. So especially for mechanical engineering students, I have a source of heat, right. So Q dot, which is heating a candle or something like that, right. This is a candle that is heating this 1D rod, right. And then I ask you to find the temperature profile after a certain time or something like that, right. So this is heating up, the heat is being dissipated right, towards both the ends. This is the boundary conditions are, this is at room temperature, this is at room temperature, right. So, the heat is being dissipated. So, at some point, you know, so the amount of heat being dissipated should be the same amount of heat that you are generating. So, you would develop what is called a steady state, right. You can solve the heat equation, which I am not going to do here, but you know, so you have, if you are really curious, you solve it. I mean, this is also an interview question, so why don't you solve it? If you are stuck, of course, now you have resources, right. So, you have all the AI resources at your fingertips, you can see how to solve this problem. It turns out the solution of this, you would expect it to be some kind of a parabola, but it is not, right. So, it is actually two straight lines like this, right. So, they have a maximum here, and you know, this is the temperature. I am drawing temperature as a function of distance, right. So, this is T max and this is at room temperature. Okay. Now, you are saying I am actually on this rod, right, on this rod which I am heating up, I am actually defining a temperature here, right. So, as T max in the steady state. This is in steady state. Steady state means amount of heat that I am putting in is the same amount of heat I am taking out. So, there is, you know, this temperature profile is not evolving with time, but there is a temperature profile, right. The temperature profile, sorry, I have to be more symmetric with these curves. This is temperature versus space or distance. This is T room temperature, this is T room temperature, right. At every point I am defining some kind of a temperature, that is why I am able to draw this graph, right. But this is not an equilibrium system, this is a system in steady state, right. So, temperature steady state means temperature profile does not evolve with time, but this is not an equilibrium system, right. If for it to be in equilibrium, you know, all temperature should be the same, right. So, it is not an equilibrium system, there is heat flow that is happening, right, and when there is heat flow that is happening, you know, so it is not a system that is in equilibrium, right. So, as per what we understand, right. So, then how are you able to define temperature, right. Now, the caveat here is, so we are talking about various different types of, you know, so I do not want to confuse you by saying, you know, different things for equilibrium, right. So, what I said earlier is, you know, so I can define temperature only, you know, if my gas molecules are in equilibrium, right. So, let us say, or here the solid, you know, phonons are in equilibrium, right. So, I take this particular volume, right. I take this particular volume and I change its temperature, or you know, let us say, so I take this volume, right. So, volume 1, I am going to call it RVE1, RVE for representative volume element, right. Okay. Now, I ask you the question, how long does it take for me to increase its temperature from TR to some T1? How long? So, these are actually heat people, people who have solved the heat equations for the temperature to increase from TR to T1. Okay, so that is the question that I ask. This is also solvable, right. So, you can solve it using heat capacity, heat conductance and other things, but there is a profile, right. So, at the RVE of interest, its temperature starts at TR as a function of time, right. So, if I look at the transients, it is going to go to T1 within a transient of some time, right. Now, so again in this transient period I am able to define temperature everywhere, right. So, essentially what I am saying is, if I am defining a temperature, right, by the time I measure the temperature, right. So, this let us say the, you know, this increase takes about microseconds time, right, just for you know, so the heat capacities are such that this increase is happening in a microsecond time, right. But by the time I measure the temperature at that time the gas molecule or the phonons in the system in this case, right, so or the gas molecules in the air, right, have already equilibrated to that temperature, right. So, initially the velocities here are are given by this Gaussian distribution. This Gaussian distribution is going to tell me that the velocities are or the standard deviation is about Tr, right. By the time I go here, it is already taking me some microseconds of time, right. In microseconds of time, so I have increased the temperature, right. So physically I have increased the temperature. The gas molecules have already adjusted, right. Already adjusted means in what time scale, right. So I have taken it from point 1 to point 2, right. So this is at point 1. I have taken it from point 1 to point 2 where the temperature is T1. It is a bit different at point 2. Let me use a different color. So this is at point 2. The temperature is T1 at point 2. T1 is greater than Tr, that is fine. But the very fact that I am able to define a T1 and a Tr, very fact means that the phonons in the system have already achieved thermal equilibrium. What does that mean? That means the phonon distribution or or the gas molecule distribution has already achieved the Bose-Einstein distribution corresponding to T1, right. So, initially the Bose-Einstein distribution was corresponding to Tr, room temperature. Then so within a microsecond is this time enough, right. So the question that we are asking is microsecond time enough for phonons to redistribute into an equilibrium configuration. This is statistical mechanics or equilibrium distribution defined by Bose-Einstein statistics. And indeed that is the case because so for phonons to equilibrate it's an instant process. It takes maybe picoseconds, at the maximum tens of picoseconds or something like that, right. So phonon equilibration is happening in let us say picosecond time scale, right. I am increasing the temperature from T1 to T2 in microsecond time scale, right. So of course at every point there is this micro equilibrium that has already developed, right. So when I say this is not an equilibrium problem, this is with respect to heat transfer. Heat is being transferred, but each of my RVEs is in thermal equilibrium, right. So since each of my RVEs is in thermal equilibrium, because so it takes a microsecond for me to increase the temperature, and within microsecond, within a picoseconds it has already achieved thermal equilibrium, right. So even if I am increasing the temperature by nanoseconds or tens of nanoseconds, I already reach equilibrium, right. So the thermal equilibriums, right. So now I am going to define equilibrium, right. So I mean overall there is some heat transport happening. So this is something is flowing, so this is a non-equilibrium problem, right. So from a heat transport perspective, but if I am just looking at every individual piece of it and then thinking of equilibrium definition from a StatMech perspective, right, every individual RVE, representative volume element, has already achieved its thermal equilibrium, right. Before so as and how the temperature is increasing from 25 degrees to 26 degrees to 27 degrees, by the time it goes to 26, even before you realize it's the distribution has already become that thing equivalent to 26 degrees, right. By the time you reach 27 degrees, the distribution has already become a distribution that is equivalent to 27 degrees, right. So the distribution equilibration is something which is much more faster than the rate at which I am transporting this heat, right. As a result, for all these heat transport equations etc., it makes sense that I can actually define temperatures at at each of these points, right. So there is an underlying assumption there, and that is true, that every individual point I can define a temperature, which means every individual point has some kind of a distribution, in this case some kind of a Bose-Einstein distribution of phonons that has already reached the temperature set by the distribution. Okay. And later on I am letting the heat flow and then increase this temperature and decrease this temperature. In that sense it is a steady state problem, right, but every RVE is already in equilibrium, right. So when we talk about things in equilibrium, right, so we allow for, in thermodynamics we allow for heat to flow out of the system into the system, etc., but once it flows into the system it comes to certain temperature, and that temperature if I am measuring it beyond a few nanoseconds or a few if I am measuring it in microsecond time scale, I can already assume that okay, so it is reaching the temperature set by StatMech. Okay. So these are things that one might have to reconcile, right. So someone coming from a mechanical engineering background will call this a non-equilibrium problem because there is heat that is flowing, right. But someone coming from a statistical mechanics background will say every individual element is already in equilibrium, and that is the fundamental reason why I am able to define temperature. Both are correct, right. So heat is flowing, yes, at a time scale which is much more than every individual element trying to equilibrate with itself, right. So that means that the gas molecules or the phonons there are trying to equilibrate with themselves, right. So it is a time scale problem. The StatMech time scale is much smaller than the heat flow time scale. So with respect to heat flow, the entire thing is in steady state. This is steady state, but with respect to StatMech, every individual RVE is in equilibrium with itself in some sense, right. So every individual phonons are in equilibrium with themselves, right, and that is what one needs to reconcile. So it is okay to define temperatures, right, especially if so the measurements that I am doing, the flow of heat is changing temperatures in a time scale of microseconds, perfect. I will actually define temperatures at every point on this rod, no problem. It is not an equilibrium, it is not a non-equilibrium problem from a StatMech perspective. Every RVE is in equilibrium with itself, right, but overall for heat transport it is a non-equilibrium problem. Okay. Okay, so let us stop there and let us begin now with laws of thermodynamics. Okay. So let us end this lecture here about equilibrium and let us begin with the laws of thermodynamics. Thank you.